Okay, so our last little portion on amines is going to just be talking a little bit about how are amines seen in nature or used in nature. So the first one that I thoroughly enjoy, because I personally do not like fish, and the fishy smell makes me nauseous every single time, but is actually how you get rid of a fishy smell. So, when you go to a restaurant or whatever, and they always give you a lemon to squeeze over your fish. And it's not because lemons taste good or whatever. It's actually because the citric acid in the lemon is going to actually neutralize that fishy smell. Grace, you're good. You're fine. So that fishy smell is caused from trimethylamine, which is this molecule here. And a citric acid molecule looks like this. So it's got lots of carboxylic acids on it, which is again found in lemon. When you squeeze that lemon on top, what you're doing is you're just neutralizing your fishy smell. So you're turning that amine into a ammonium ion, and that ammonium ion is then odorless, so we can't smell it anymore. So it gets rid of that fishy smell and taste in your food. So that's one use of these reactions that we're learning in real life, is just whenever you eat fish. Additionally, a lot of drug molecules have nitrogens in them or amines in them, and they're almost always sold as the actual HCl salt is what we call it. So the molecule, the drug molecule plus HCl. So that ammonium salt that we've been talking about is how those drug molecules are sold. And part of this is because that is more soluble in water. So it helps increase the solubility when you digest these molecules. So that when you, like, for example, this is Benadryl here. So Benadryl is also a molecule that you often see in like a liquid form, right? And if it weren't in a liquid form, this would not mix with water, and then it would be kind of gross to be drinking like an oil, right? So like kids Benadryl and stuff like that, they make it into the salt version, so it's soluble in water and you're able to drink it. Or even if you do take the pill form, it's still in that salt form, so that when it gets into your stomach, it can dissolve easier and get into your bloodstream easier. So pretty much they almost always use chlorides for this as your counterion. So if you see like molecules, a lot of them are over the counter, but if you see a lot of molecules that, or drug names on the bottles you're looking at, and it says chloride at the end, it's almost guaranteed that it has an amine in it. Additionally, why not talk about cocaine? Everybody's favorite illicit drug. I don't know. So cocaine is extracted from kuka leaves with an acidic solution. So the leaves where you get cocaine from, if you grind those up with and then add acid to it, it makes the salt version of cocaine, and that's how you actually isolate it. Is you dissolve that, now dissolves in water, so then you can just take the water and wash it and then evaporate all the water off, and then you have your cocaine. And everybody's heard, or I don't know if everybody's heard, I guess my middle school health teacher taught me about crack cocaine and how it affects people more, it has higher efficacy with your body. But I had never actually known the chemistry behind it. I mean, why would my middle school teacher teach me the chemistry of cocaine? I don't know, but you're learning it in college because that's what we do. So what happens to make crack cocaine is a process called freebasing. So if you add base back into your ammonium ion or ammonium salt that you made, you then take that hydrogen back off. It's kind of a competition between who wants to have that proton. So if you put something more basic in there, the more basic thing will steal the proton and leave you with your amine. So crack cocaine is then just the amine form of the ammonium chloride that was isolated. So typically you heat this when you do it, and it makes a crackling noise, so that's why it's called crack. And then for additional information, typically you don't actually use sodium hydroxide, since sodium hydroxide, if you have any base left in there, it's pretty toxic. It pretty much destroys your cells really quickly. What they'll actually do is use baking soda, which is also a base. They'll use baking soda, and it bubbles a bunch and makes that crackling noise, and then it will solidify on the top, and then they like just flick off the solid, and that solid is the base that they don't want, and then they're left with the crack that they can inject into their bloodstream or whatever they do. I guess that's what they do. I don't know, but that is all about crack. There you go. Now you guys know more about crack. The last thing I was going to talk about is heterocyclic amines. So we don't necessarily just have to have amines with alkyl groups on it. We can have lots of different things, and we can have them in cycles. And these are super duper duper common. I think it's something like 96% of pharmaceutically active molecules have some kind of nitrogen heterocycle associated in them. They're so common. They're kind of hard to make, to be honest. And that's part of why like pharmaceutical molecules are so expensive, is because they're a little tricky. So these are a lot of different versions. So pyrrolidine is a 5-membered ring with a nitrogen in it, or you could put double bonds in there and make it pyrrole. Or if you have 2 nitrogens, but the 5-membered ring, it's called an imidazole. You also have the pyridine, which is the 6-membered ring, pyridine, which is kind of like a benzene ring, but now has a nitrogen in it, pyrimidine, which has 2 nitrogens, or purine. So pyrimidine and purine are both molecules that we'll be revisiting soon-ish, in like a month, because they're major components of DNA and RNA. So there's millions and millions and millions and millions of these in your body right now. And then an example of just a drug molecule that contains these very common heterocycles is nicotine. So in cigarettes, or your favorite version of wherever you get nicotine from, has 2 of these different types. So we have here, we have a pyridine, and then here we have a pyrrolidine. So you see these everywhere in real life and in pharmaceuticals, drug molecules, everything.